Greetings, AP Chemistry students. Today we're going to talk about the reaction quotient, Q. And the reaction quotient is what's going to allow us to determine which direction a system is going to have to shift in order to achieve equilibrium. And Q is calculated using the law of mass action. In other words, it's the same way we write an equilibrium expression, but you can calculate Q at any time during a reaction. In fact, Q is typically used when you are starting with some set of conditions and you're trying to determine, am I at equilibrium? And if I'm not at equilibrium, which way do I need to shift to reach equilibrium? Now, when you calculate Q, if Q equals your equilibrium constant, since they're both calculated the same way, then you're already at equilibrium, and so no shift in the reaction will occur. If Q is larger than K, then the system will shift to the left or to the reactant side. Because if you're not, if Q is larger than K and both of these are calculated with products over reactants, if Q is bigger than your equilibrium constant, you have too many products, not enough reactants. And so the reaction needs to shift back to the reactant side in order to change that ratio and get it to equal the equilibrium constant. You've got too many products, not enough reactants, so you need to turn some of those products back into reactants to achieve equilibrium. So if Q is larger than K, it shifts to the reactant side. And as you might would guess, if Q is less than K, the system will shift to the right or to the product side because the numerator of your reaction quotient is too small. You need more products, less reactants. So let's take a look at a problem to solve. We have this reaction right here that says nitrogen plus 3 hydrogens makes 2 ammonias. And it says for the synthesis of ammonia at 500 degrees Celsius, the equilibrium constant K is 6.0 times 10 to the minus 2. And keep in mind, for this reaction, if we were trying to write the equilibrium expression, K would equal the concentration of NH3 squared over N2 times H2 cubed. And that equals 6.0 times 10 to the minus 2. In other words, 0.06. This says predict the direction in which the system will shift to reach equilibrium in the following cases. And so it gives us these concentrations. So we need to calculate Q. And on an AP exam, you need to actually show yourself calculating Q and comparing it to K. So Q equals NH3 is 1.0 times 10 to the minus third. And we would square that over 1 times 10 to the minus fifth times 2 times 10 to the minus third cubed. And if we plug this into our calculator, 1 times 10 to the minus third squared, we get 12,500,000. Or essentially, if we round this off to significant figures, we get 1.3 times 10 to the minus, not minus, times 10 to the seventh. Okay? So in this case, Q is greater than K, so it will shift to the left or reactant side. In other words, this number right here is way larger than 6.0 times 10 to the minus 2. So we have too much of the stuff on the top of the fraction, the NH3. We have too little of the stuff on the bottom. So the reaction needs to run in the reverse direction to reach equilibrium. So let's take a look at part B. We plug in Q equals 2 times 10 to the minus fourth squared over 1.5 times 10 to the minus fifth times 3.54 times 10 to the minus 1 cubed. And let's plug that into our calculator and see what we get. And when I calculate this, I'm getting, it says or 6.0 times 10 to the minus 2. Q equals K, so no shift. We are at equilibrium in this case. And then let's look at this last scenario. Q equals, well, it's going to be 1 times 10 to the minus fourth squared divided by 5 times 1 times 10 to the minus second cubed. So let's plug that into our calculator and see what we get. And I'm getting 0.002 or 2 times 10 to the minus third. Q is less than K, so it will shift to the right. In other words, it will make more products. So I hope this gives you a little bit of a better understanding about how the reaction quotient Q is calculated and what it's used for. And then tomorrow, we're going to use this to actually help us in solving some fairly complex equilibrium problems. That being said, hope you'll have a great day.